All right, chemistry. This is the quiz preview for the quiz coming up on Friday, November the 15th. And this is due on Friday, November the 15th. It's extra credit, it's optional, but you get up to 25 points for doing this. Okay, those are extra credit points. All right, I would recommend you do that. Extra credit points actually help your grade more than regular points do. Okay, so what I'm asking you to do is draw the Lewis dot structure for each of these compounds, determine the Axe notation, use page 15 in your packet to indicate the domain geometry, that is the family and the molecular geometry, the shape. Determine the hybridization of the atoms indicated, and I might ask you to also write the Aufbau structure for the hybridization. Okay? Let's go ahead and do that. Okay, so first, either go back to the Lewis dot structure lesson. Don't remember what day it is, but it's titled Lewis dot structures, and write down the rules if you don't have them memorized. You have to have these memorized. They don't give them to you on the AP, and I'm not going to give them to you on any tests. So first you count the valence electrons in all the atoms that you're working with. Place the atoms symmetrically, that is evenly, with the least electronegative atom in the center. Remember, hydrogen cannot be a central atom because it can only bond on one side. 3. Form single bonds between the central and outside atoms. 4. Create octets around the outside atoms. If you still have electrons left over, place the remaining electrons as lone pairs around the central atom. And then finally, you need to rearrange them. So the two things you need to achieve is all of the valence electrons that you counted in step 1 have been used, no more, no less. And second, that all atoms have an octet. Okay, so let's go ahead and do this one. So carbon dioxide, I'd recommend you use as much space as you can. So start way over here doing this. Carbon dioxide is going to have 16 electrons. If we place these symmetrically with the least electronegative in the middle, so we're going to be here. Create octets. Now I can't do that because I'm writing in pen. So I'm just going to go ahead and go to the final product. Be sure you knew how to do that. You would have placed octets around, then you would have seen you needed double bonds in the middle. Okay, that's the Lewis dot structure. There's a dot right there. All right, now determine the Axe notation. So Axe only applies to the central atom because that's what determines geometry. So the Axe notation for carbon is AX. It has two bonding domains. That's what the X's are. 1, 2. Double bonds still count as one bonding domain or one electron domain. And it has no lone pairs around the carbon, so it's E0. And you go to this sheet, you find AX2E0 is linear. It's linear and linear. Domain is linear. It's in the linear family, and it's linear domain geometry. Okay. So that means it's going to be linear, linear. And I'll just abbreviate some of these. Linear, linear, like that. Okay. Then it says that's the Axe used to determine the domain geometry and family. We did that. Determine the hybridization. So hybridization for carbon. It has 2 electron domains, or a steric number of 2. Steric number means the same as electron domain, so if you look at it right here, it's 2. So that's sp hybridization. Okay, so you built a carbon dioxide model, so this is sp, and each of the oxygens has got 1, 2, 3 electron domains. So that's a steric number, and we're going to abbreviate that SN, steric number of 3. And if you come back here, a steric number of 3 is sp2. Okay, and if I asked you to draw the Aufbau structure, I won't do it for all the atoms, but let's say I asked you to do it for carbon. We said it's sp, so that's going to look like this. It's in the second row, but I don't care if you put the 2. It's sp. Whenever you have sp, you have 2 of them. Okay, and then you have an unhybridized py, and an unhybridized PZ. So that's where the double bonds form with carbon dioxide, okay? So that's how you do that. Let's go on to another one, BH3. Go to your periodic table. Boron has 3 valence electrons, so that's a total of 6. So when we draw that symmetrically, it looks like this, unless you draw the H's first. It doesn't matter which side you put the H's on, just do it like that. You could put one on the top instead of the bottom. It doesn't matter, okay? There. Okay, and it's 6 and 6, so everybody has an octet. This is an exception to the octet rule, okay? Okay, B has 6 for an octet. Okay, so boron, it's AX3E0. Come over here. AX3E0 is right there. It's trigonal planar. And let's just go ahead and do this. It has a steric number or electron domains of 3, so it's sp2. You can just do all that at the same time, okay? Same family, same shape. Anytime the E is 0, it's going to be the same name. And this is sp2. Steric number, I should have written that. So steric number, Sn, steric number, that's how many electron domains? 1, 2, 3 of 3. Okay? There you go. And again, if you were going to draw that, it would be this. And then the unhybridized PZ, which can form a double bond, but it doesn't have to. It just has the ability to, okay? There we go. All right, let's keep going. Draw it. Let me put a little line here. Okay, and we put octets around this oxygen and around this oxygen. And I think I'm going to do it. I want to be sure, I'm being thorough. Okay, so I don't want to set a bad example. So the next rule is create octets around the outside. I'll do it lightly because I know I'm going to erase some of them. So now I have 8 here and 8 here. That's 16. I need 18. So I'm going to put the additional 2 as lone pairs on top of the sulfur. So now I have 18, but sulfur doesn't have an octet. It only has 6. So anytime that happens, you're going to take some lone pair from somewhere. I'm just going to choose these 2, and I'm going to put them in as double bonds. Okay? And while I'm not testing you on resonance structure, this is a resonance structure. You could have put the double bond on this side, okay? But anyway, that is it. So now we've got to look at the Ax notation only for the central atom, and it's got 1, 2, 3. Well, it's got 2 bonding domains and 1 lone pair. So it's going to be AX2E1. We come over to our sheet, and that is trigonal planar family bent shape because it has those 2 lone pairs that are pushing down on these bonding domains there. Okay, so you have to write 2 different names here. Okay, and we can use the same sheet. We can come over here and say that's a steric number of 3, and that's sp2 hybridization. And again, if I were going to draw that, again, each one of these has its own hybridization. So I'm not going to get into the outside atoms, but it would be this. Okay, so sp, that means spp. So you have 2 different p sections plus the s. That's a total of 3. That's that number there. So 1, 2, 3. Okay, so you're going to have 1, 2, 3 of those. All right, let's keep going here. CH4. Okay, they used all 8 electrons. Everybody has an octet. Forgot that one. Let's put that in. Everybody has an octet. Carbon has 8. Hydrogen has 2. That's all it can take. Okay, so that's going to be for carbon. It's got 1, 2, 3, 4. So the AX notation is 4 bonding and no lone pairs. Come over to the sheet. AX4E0 is tetra, and it's got a steric number of 4, and the hybridization is sp3. And this is the Aufbau structure for it. They're all on the same level for this one. Okay, there you go. So NH3, ammonia, same kind you have in your house. 8 symmetrically, and lone pairs on the central. And we've used all 8. There it is. So AX number for the central atom, it's got 1, 2, 3 bonding and 1 lone pair. And you come over here again, you're going to get to use this sheet on the test, not on the AP though if you're taking the AP. It's a tetrahedral because it's got 4 electron domains, steric number 4, but the actual shape is trigonal pyramidal, okay? That's when you take your 3 fingers and you put them down like that. Here's the nitrogen, down at my fingertips are the hydrogens, okay? Trigonal pyramidal, okay? And steric number is 4. That's the total number of electron domains. 1, 2, 3, 4, both bonding and lone pair. You can just add these 2 numbers here. Okay, and that's going to give you sp3. All right, and that's the same one we saw for up here for CH4. Okay. Okay, H2O we've done a bunch of times before. Okay, that's drawing it very symmetrically. So you've got 4 there, you need 4 more to get 8, so you put them as lone pairs here and here. So AX notation, you got 2 bonding pairs and 2 lone pairs. Okay, so you bring this over, and that's going to give you AX2E2 is tetra family because there's 4 total electron domains. But AX2E2 gives you a bent molecule. So steric numbers, total number of electron domains, both bonding and non-bonding or lone pair, 1, 2, 3, 4. And that's going to be sp3. And it's the same. It's the same as this one. I don't know what time I thought I drew one down there. Anyway, it's the same as this one, okay? All right, so that's the same, that's the same. All these are sp3s, so I don't need to draw that again. Okay, keep going. Now we've got one that's going to be an expanded octet. Okay, so phosphorus has 5. There's 1 phosphorus times 5. And there's 5 fluorines. And fluorines have 7, so we got a lot of electrons here. And that equals 40. So when you draw this, especially these expanded octets, kind of spread things out so your electrons don't look so crowded. So it's going to be P. Now this one, you got 5 of the F. So you kind of draw it, you can't draw it, one side, the other side. So you're going to kind of draw it like a star. So F. Put them way out here so you have a lot of room for your electrons. Okay, so we've got single bonds here, 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 and there. Okay, so that's 10 electrons to go around that. Now you got to create octets around all the fluorines. Okay, and you want to kind of be careful how you do it so you can tell which atom they belong to. So there's 8. There's 8. It kind of looks a little spread out, but it's good. It's good to do that actually. Okay, and if I count 8, 8, 8, 8, 8, that's 40. That's how many I need. Everybody has an octet. Phosphorus has an expanded octet. Okay, so we're going to write the AX notation. So we're interested in phosphorus. It's AX5. Has 5 bonding locations and no lone pairs. Okay, so we have to flip over to the back side of the page. There it is right there at the top. So it's trigonal bipyramidal, trigonal bipyramidal. Again, it's a right side up three-sided pyramid and an upside down three-sided pyramid. So that's the bi part of it. There's two three-sided pyramids, okay? Again, you can abbreviate these names. Oops. Trig bi, and then there's where I meant this slash trig bi. Okay, so same name because there's a zero there. All right, and what's that going to be? Okay, so it's one we haven't talked about a lot. Now, I'm going to tell you something. On the AP, they say they don't look at hybridization of expanded octets. They will look at the geometry. They will ask you that. So they'll ask you trig bipyramidal, trig bipyramidal, but they will not ask you this, but I'm going to still have you do it anyway. So remember, the sp3 fills up. That's four. That's a tetra. That's 4 steric number. And then the fifth one, the extra set of electrons goes into the D subshell, so it's like a storage locker. So it's going to be, again, you just need to read this off this sheet right here, okay? It tells you everything you need to know to answer this question, okay? All right. Okay, keep going. Okay, so we have 34. We've used 8 of them. Octets around everybody on the outside. Okay, so it's 4 times 8 is 32, but we need 34. So I'm going to draw a little arrow out here. There's going to be a lone pair on that sulfur. It's another pair. I'm going to draw it out there. You can do that too. Just make it clear. So that's a lone pair, okay? So what's this going to be for the sulfur? It has 4 bonding, 1, 2, 3, 4, and 1 lone pair, E1. Okay, so we come back to our sheet. There it is. It's got 5 electron domains, steric number of 5, so it's still trig bipyramidal, but you took off one of them. You took off one of these axial, like this one right here, and you turned the thing on its side, so now it looks like that, so that's a seesaw shape. Steric number is 5, and that means it's going to have also, like the last one, sp3 D. You could put D1 if you want, but it's just D, okay? That would be the hybridization of this one. Next. Okay, so this gives us 8. 8 is 24. We need 28. So the last two have to be 2 lone pairs on the central atom. So these are 2 lone pairs, okay? I'll just go ahead and leave that. I think that's clear. So let's look at the central atom. It has 1, 2, 3 bonding domains. So A, X, 3, E, and 2 lone pairs, 2. Okay, so that's AX notation. We come over here and we see it's still part of the trigonal bipyramidal because it has 5 steric number of 5 electron domains, just like the previous 2. So this one's a trigonal bipyramidal family, but it's a T shape. You're taking off 2 of these, so it forms, if you just look at this like that, it looks like a T. All right, so that's going to be, it also has that, and that's going to be trig bi and T shape. Okay, there you go. And if I were gonna, we're not gonna get into drawing the Aufbau for these. Okay. Okay, so let's go. Let's keep going. Okay, again, you got to kind of make a star shape. I'll see if I got enough space to do that. Didn't give you very much space, but you. So 5 bonding domains, and we're just going to try to quickly put lone pairs, complete octets, in other words, around the other fluorines, around all the fluorines. Okay, so that's 5 times 8 is 40. I need 42. So you're going to need, where can I draw this? I'm going to draw an arrow out there and do that, and that's a lone pair, LP. Lone pair goes there, somewhere in between those there. Okay, so what's that going to be? AX5E1. So we come over here. It's right there. It's an octahedral family, and it's a square pyramid. It's like an Egyptian pyramid. It has 4 sides. Okay, it's got 6, steric number of 6, and there it is, sp3. And then 2 of those lone pairs have to be stuck. Excuse me, 2 of the electron pairs have to be stuck in the D subshell up there. And steric number is 6. That's the number of total electron domains. And I think that's all there is to that. Okay. All right. Again, I'm not trying to do any outbows with extended octets. Okay. Here we go down here. Let's try to... Okay. Here's that unusual one, which has a noble gas that can form bonds. So that's going to have 8 valence electrons. There's 1 times 8 equals 8. And then the F4. Again, notice the sequence in which I'm building these, okay? Don't skip steps. Just go ahead and do them the way I'm doing them. So now I'm putting the completing octets around all the fluorines. Okay, so we have 8, 8, 8, 8. 4 times 8 is 32, but 36 you got to have. So that means you need 2 more lone pairs. So I'm going to draw a lone pair right here. That's a lone pair, and one right here. That's a lone pair. So the AX notation is AX4 because you have 1, 2, 3, 4 bonding with the fluorine. And I think I should have done what I did last time. Let me erase those lone pairs. Okay. Let me draw an arrow out here away from it so you can see them. There's a lone pair. And draw an arrow out this way. There's a lone pair. So 4 bonding, 2 lone pairs, so that's E2 for the lone pairs. Okay, that's going to be octa, and it's going to be AX4E2, so we come over here. Okay, and it is right there, and it's a square planar. Okay, so it's going to actually be a flat square molecule. Okay, and that is sp3d2 hybridization. Okay, there we go. All right, so now I'm going to come down here. We're going to do this. Okay, it's NO2 but with a minus sign. And then you have 1 extra electron. So that's going to give you 18. Okay, create octets. That gives you 16. You need 18, so we're going to put the other 2 up here. So everybody has an octet except nitrogen, so you're going to take 1 lone pair from one side and stick it in between. So now everybody has an octet. Be sure that's erased. Okay, so this is a resonance structure. The double bond could be on this side or this side. Okay, we're not going to deal with resonance structures on this quiz. It's just, that's it. Okay, all right. So central AX notation. So there's 1, 2 bonding domains. The double bond, the single bond. Those are bonding. Then the third is the lone pair. So the steric number is 3. 1, 2, 3. Okay, so now we get to go back to the other page. It's AX2E1. It's right here. It's a trig planar family, and it's bent. Let me get that clear. Trig planar and bent. And the steric number's 3, and it's sp2 hybridization. Okay, and what else do I need to write? Oh, sp2 hybridization. Okay, again, how do you do it? You got 2 plus 1 is 3. That's the steric number. So that's spp SP. The PX and the PY get hybridized. So S, PX, PY, that's a total of 3. Okay, so that's how you get SP2 if you have to do it from memory. All right? So how do you do this symmetrically? It's got to have 2 central atoms, O and O. H's cannot be in between other atoms, so it's going to look like that. Okay, created single bonds. We need 14. Hydrogen already has octets. 2 electrons is all a hydrogen can take. So now you start creating lone pairs here, here, and here. And if you count, you have 14. Okay, so that's what it looks like. All right, so you take each of these O's one at a time. But as you can see, they're both identical. They're symmetrical. They look exactly the same. So let's just go ahead and write the ax notation for either one of them. Let's just do the one on the left. It doesn't matter. So it has 2 bonding. That's a 2, and 2 lone pair. Okay, and remember, you're talking about lone pairs, not lone pair electrons. Okay, unlike a formal charge, you actually want to know how many pairs. So it's 2 there. Okay, so we've seen this one before. It's like a water molecule. It's right there. It's tetra, and it's bent. Okay, and the hybridization is, it's tetra, so it's 4 steric number and sp3, just like a methane molecule, CH4. Okay, I don't care where you write all this stuff, try to keep it kind of organized. Now, if I were to draw this, since this is bent, so it's bent between this hydrogen and this oxygen, and then it's also bent between this hydrogen and this oxygen. We saw this in class, so I'm going to go ahead and write a hydrogen here. I'm going to write an oxygen up here. The other oxygen comes down here, so there's the bent for this oxygen. Now this is going to bend upward like that because the electrons want to get as far away from each other as they can. And so that's what the molecule would look like. You don't normally, I'm not going to ask you to diagram them, but just so you see what that's going to look like, okay? All right, I don't want to risk that this video is going to fail or I'm going to lose all this work. It's just the way this software works sometimes. So I'm going to end this. Some of you may feel like this is all you need, but I'm going to continue with number 14 and go to the end on a different video. So if you want to watch that, it'll be coming up here pretty soon.